So we're asked, what is the whirling speed for a light propeller shaft of diameter 25 millimeters, supported in flexible bearings 0.8 meters apart, when carrying a propeller of mass 10 kilograms at its midpoint? If the propeller has an eccentricity of 0.5 millimeters from its geometrical axis, what will be the range of speeds for which the deflection will exceed 2 millimeters? The tensile modulus for the shaft is 200 gigapascals. Assume the static deflection of the beam can be determined from the following formula. Okay, so what have we got? So this is our shaft. It's the propeller is centered on this shaft, and it has a mass of 10 kgs and eccentricity of 0.0005 meters. The length of the shaft is 0.8 meters, and we're told that the deflection, what are the speeds at which the deflection is greater than 0.02 meters. Okay, so the deflection, this deflection here, this formula, this comes from the deflection of beams. So a beam that has a load in midpoint, that would be the deflection. I'll cover that in another video, or in a future video. So we want to work out what this deflection is first. So in the deflection we have this value I is the second moment of area, and the second moment of area for a circular section is pi d to the power 4 over 64. That is, we get that from tables. I may have derived that in a previous video. So that is my second moment of area. And then the deflection then is m. Well, the m is 10. The length of the shaft is 0.8 meters. 48 is just 48. E, we were given, is 200 gigapascals, or 200 by 10 to the power 9. And this is I. So when I put that into the calculator, I get my deflection to be 27 micrometers. Okay, so the critical frequency then, or the frequency with which whirling occurs, is 1 over 2 times square root of the deflection, and 1 over 2 times 27 micrometers is 94 hertz, and converting that to radians, just multiply by 2 pi, gives me 595 radians per second. Okay, so that's omega c. So the deflection then is E over omega c squared divided by omega squared minus 1, and we're looking for omega. So the eccentricity we were given, that's this value here. We just calculated 595, we want omega squared 1, and we were told that the deflection y was when it was greater than 0.002 of a meter, or 2 millimeters. So we have y. So I'm just going to bring this up here, and we have 595 squared all over omega squared minus 1 is equal to plus or minus. Okay, so this deflection y, it can be in that direction, or it can be in this direction. So we're just using plus or minus. And 0.005, that's the same as 5 over 20, which is the same as 1 over 4. So bringing the 1 across, we have 595 squared over omega squared is equal to 1 plus or minus a quarter. Okay, so 1 minus a quarter is 0.75, so omega squared is 595 squared divided by 0.75, and that gives me omega equal to 687 radians per second. And 1 plus a quarter is 1.25, so 595 squared divided by 1.25 is equal to omega squared, and from that omega works out to be 532 radians per second. So the deflection of the shaft, like we were told omega c, or not we were told, we calculated, omega c was equal to 595. So that's the whirl speed. So this is when it's, you know, theoretically it deflects to infinity. But any value between these two ranges will give us a deflection of 2 millimeters. Yes, 2 millimeters. Okay, we'll go on to the next example.